Today we want to talk about calorimetry, which is a method, an experimental method that will calculate how much heat is being absorbed or released in a system. When we do calorimetry, there are two basic types. One is a coffee cup calorimetry, sometimes known as constant pressure calorimetry. And that's the kind that we're going to be doing in the labs and the type that's normally done in labs. At least high school and college labs. Bomb calorimetry, which is constant volume calorimetry, is when weighed reactants are placed inside of a rigid steel container and ignited. In either case, we're dealing with actually what how much heat is produced in this case and heats up water inside these containers. That water is actually measured for its temperature change, and then we use calorimetry, usually a form of MCAT, the MCAT equation, in order to calculate the amount of heat released. So when we look at these equations, keep in mind that in any thermochemical reaction carried out on a calorimeter, the heat lost by one part of the system is going to equal the heat gained by another part of the system. So the amount of heat produced by the reaction or given off by the reaction is the amount of heat absorbed by the calorimeter, and the calorimeter itself is going to absorb that some of the heat, and then the amount of heat absorbed by the solution added to that. So MCAT defined the heat absorbed by the solution. Sometimes I refer to it as kitty cat for the heat absorbed by the calorimeter. Now, a lot of problems will just tell you to ignore the calorimeter, or they won't even mention it. So if it does that, then we're just dealing with Q total equals the Q of the solution. But when we are dealing with a situation where they do want us to include the calorimeter, this is the equation that we will use. K sub Cal is the heat capacity of the calorimeter, and that's going to be in joules per degree Celsius for that container, that whole container. Specific heat is joules per gram degree Celsius, so they'll look at a material by how much mass it is, but since the calorimeter is an object that is containing the reaction, they just think of that whole object as being dealing with the amount of heat that it's going to gain per degree Celsius that the water temperature inside it changes. So when we see a question like this, for example, it says 3.358 kilojoules of heat are added to a calorimeter that contains 50 grams of water. The temperature of the water and the calorimetry, originally at 22.34 degrees Celsius, increases to 36.74 degrees Celsius. So there's our delta T. Calculate the heat capacity of the calorimeter in joules per degree Celsius. So our total Q, and sometimes we'll leave off that negative if we're just going to think about the fact that the heat here in this case is going to be absorbed by the calorimeter. The Q of that that is added to this, let's say Q total, is going to be equal to the Q of the calorimeter, the heat of the calorimeter, remember, plus the heat of the solution. And it just told us that they were going to add 3.358 kilojoules. Now, look at your value that you want your calorimeter constant in joules per degree Celsius. So we'd be better off just to go ahead and change this to joules in the first place. So let's just say that this is 3,358 joules of heat. Q of the calorimeter, remember, is going to be the calorimeter constant times delta T, so K sub Cal, and that's what we're looking for, is the calorimeter constant. So the calorimeter constant times delta T. Now if we look up there, delta T is going to be 36.74 minus 22.34. So we end up with a delta T of 14.4 degrees Celsius. And remember, and I'm going to just write this above so that hopefully it will help you start remembering what the formulas for these are. Kitty cat and MCAT. Not a capital M, just a lowercase m. So we need the mass, and it told us the mass was 50 grams for the water. The specific heat of water is 4.18 joules per gram degrees Celsius. And we've got the same temperature change. That temperature change is the same for the calorimeter and for the solution that it contains. So when I work this out, I end up with still the 3,358 joules, calorimeter constant times the 14.4 degrees Celsius. And when I multiply all of this out, I end up with 3,009.6 joules. Because my grams cancel, my degrees Celsius cancel. So I'm left with 3,009.6 joules. Adding that to the other side of the equation, adding or subtracting from both sides, I guess you could say, I end up with 300. When I subtract that from both sides, I end up with 348.4 joules equal to calorimetric constant times the 14.04. So remember, all I did was subtract the 3009.6 from both sides. Now I'm going to divide both sides by 14.4 degrees Celsius, and I get a calorimeter constant of 24.2 joules per degree Celsius. Now, what does that mean? Because we find these values and it's like, okay, we got this 24.2 joules per degree Celsius. What does that mean? What it means is that when we look at this calorimeter, every time we increase a 1 degree Celsius in temperature for that system, 24.2 joules of the heat involved in that change is going to be absorbed by the calorimeter itself. We need to know that so that we can include that in any further calculations that we're going to do with that particular calorimeter. And when we do a lab over this, that's the first thing we're going to do is figure out the calorimeter constant for our particular calorimeter. The next example says that we have a 28.2 gram sample of iron heated to 99.8 degrees Celsius and placed in a coffee cup calorimeter that has 150 grams of water at 23.5 degrees Celsius. What's the final temperature of the system? Okay, when you have a situation like this where you are you're not doing a chemical reaction, you're simply putting two substances together that are at different temperatures, then what we're talking about is one of these substances, and we've got iron as one of the substances and water as the other substance. One of them is going to gain heat and one of them is going to lose heat in the system. They're going to meet somewhere in the middle, temperature-wise. The first thing you need to do is to decide which one's gaining in heat and which one's losing. Well, if we've got 28.2 grams sample of iron that's heated up to 99.8 before it's dropped in, and the water started at 23.5, hopefully common sense tells you that the iron is going to lose heat. That's going to be where the heat loss is occurring. And since water starts at 23.5, it's going to increase in temperature, so it's going to gain heat. So when I write this equation, I'm going to start out by saying that we have a system where one side is going to lose heat and the other side is going to gain heat. And we just said that the loss of heat was going to be the iron and gaining heat was going to be the water. Now both of these are MCAT. Both of them are simply calculating Q for each one of them. So we can say this. Now notice something else. Did it ever mention a calorimeter? No, it didn't. So we don't have to worry about the calorimeter part. All we have to worry about is just the two substances. So now that we know this, we're going to just start plugging in values for it. We know that iron was a 28.2 gram sample. It very nicely gave us the specific heat of iron, which was 0.45 joules per gram degrees Celsius. The temperature change, final minus initial, the temperature change is going from 99.8 to some final temperature. Again, I'm going to emphasize that delta T is the final temperature minus the initial temperature. Well, they gave us the initial temperature. What we're looking for is the final. So we don't know final, but we do know the initial was 99.8 degrees Celsius. The other side deals with water, and it told us that we had 150 grams of water. I know 0.0, we'll use the original sig figs here in a little bit, but 150 grams of water. Specific heat of water is 4.18 joules per gram degree Celsius. And for water, final minus initial is going to be, once again, our T sub F, we don't know what that is, minus our initial temperature, which is 23.5 degrees Celsius. So there's our equation. So let's combine our terms, okay? First of all, on the left-hand side, we've got negative 12.69. When we multiply the numbers together, negative 12.69. And that's going to be times our T, and I'm going to drop units for right now because they'll just get confusing if we keep trying to put them in the problem. They'll just get in the way of numbers and you'll start getting more and more confused. The 150 times the 4.18 on the other side gives us 627. And that's times T sub F minus 23.5. The next thing that I would do is to divide both sides by 627. So if I divide both sides by the 627, we can, whoops, not 625, 627. Of course, reduces to 1 on the right-hand side. And I end up with negative 0.0202 times T sub F minus 99.8 equal to T sub F minus 23.5. So now I'm going to add 23.5 to both sides. I'm sorry. The first thing I'm going to do is to multiply through. I end up with, I got distracted, sorry. I end up with negative 0.0202 times T sub F. And since I'm multiplying a negative times a negative, I end up by changing that to a positive 2.02 when I multiply that. T sub F minus 23.5. Now I'm going to combine terms. Now I'm going to add the 23.5 to both sides. Which of course reduces it to 1 on the right-hand side. And we end up with negative 0.0202 times T sub F plus 25.52 is equal to T sub F on the right-hand side. And now I'm going to combine the T sub F's by adding the 0.0202 T sub F's to both sides. which of course reduces it to 1 here. I end up with 25.52 is equal to T sub F, sorry, 1.0202. Remember, I'm adding this to 1 T sub F, so 1.0202 T sub Fs. And finally, my final temperature, T sub F, is going to be, as I divide both sides by 1.0202, 25 degrees Celsius. 25.0 degrees Celsius. Now, I hope you've realized that setting these problems up is the easiest part. The difficulty lies in simply doing the algebra. And as much as we need to know how to do, or, as much as we've probably done the algebra over and over in the past, we seem to forget it and we quit using our skills and we do really badly on these types of problems. So you're really going to have to concentrate on the algebra part of these problems if you want to be successful on them. So, okay. Our last calorimetry problem deals with mixing two solutions together and which is going to create a chemical reaction. It says we're going to mix 50 milliliters of 0.4 molar copper 2 sulfate at 23. Notice that the temperatures are the same all the way through, 23.35 degrees Celsius. And it's mixed with 50 milliliters of 0.6 molar sodium hydroxide in a coffee cup calorimeter. After the reaction occurs, the resulting mixture is measured to be 25.23. So we're going to have a nice temperature change there. The density of the final solution is 1.02 grams per milliliter. That's going to be important to us. That's a nice little conversion factor we can use. Calculate the amount of heat involved. Assume the specific heat is the same as that of pure water. So we're going to have the 4.18 joules per gram degree Celsius. Now it says to note the calorimeter constant from the first problem. And remember the calorimeter constant was 24.2 joules per degree Celsius. So make sure you pay attention to that. Now we're going to, by them giving us that information, we know we have to include this in the problem. So it wants to know the amount of heat involved. So we're trying to find the Q involved in this system. So the total Q is going to be the Q of the calorimeter, which remember is kitty cat, K sub cal, our calorimeter constant times delta T, plus the Q of the solution, which is our MCAT. So the total heat of the system is going to be, again, this. Now pay attention to what it tells you in the problem. It tells you that you have 50 milliliters mixed with 50 milliliters. We have 100 milliliters total of solution. It also tells us that the density of the solution, we need MCAT, right? We need a mass. So the mass of the solution we can get by taking that volume and realizing that the density is 1.02 grams per milliliter. So with that information, we can see that we have 102 grams of solution. So that's one piece of information that we're going to need. Now the kcal from the other problem, remember, was 22.4 joules per degree Celsius. Our delta T is going from 25.23, subtracting out, that's the final value, subtracting 23.35, and we end up with a 1.88 degrees Celsius temperature change. We just established that it was 102 grams for our mass. Same 4.18 joules per gram degree Celsius as that of water, as it told us, and our temperature change is still 1.88 degrees Celsius. When we multiply this out and add it together, we end up with 847 joules of heat involved. Now the last thing it wants to know, that's the amount of heat that was evolved. The last thing that it wants to know, and this is given off by the way, is how much heat was produced per mole of NaOH. Well, how do we get moles? Well, over and over we've said milliliters, or excuse me, liters times molarity gives you moles. And it tells us that we have 0.050 liters times our 0.600 molar solution is going to give us a number of moles of 0.03. So that's how many moles we're dealing with. We just established that if we have 0.030 moles, that we have, with that 0.030 moles, we produced 847 joules. So the question is, if we want that molar heat for 1 mole of NaOH, then how many, I almost put the X on top. If we've got 1 mole of our substance, how many joules do we have? So if we cross multiply, we end up with 0.030x is equal to 847 joules. So it looks like our molar heat capacity is going to be 28,233 when we divide both sides by 0.030. 28,233 joules, which is 28.2 kilojoules per mole, per 1 mole. So that's our value for our amount of heat given off per mole of sodium hydroxide.